Welcome. So I'm starting this new series on data structures and algorithms. Now, this isn't going to be a series where I just talk about a basic algorithm and give a wacky or hacky implementation out there and just explain things. No, this is not really going to be a beginner-friendly implementation and explanation of data structures and algorithms, but rather what I want to achieve with this series is creating or rather implementing algorithms and data structures in a way that can be used itself as a library. Also, we will be building the library throughout the series. Also, like I want to things like efficiency and neat and tidiness of our code in mind. All right, so if we are going to design it, and also we'll keep an idea of efficiency, whether like we are not going to like I'm not saying that we are trying to build the most efficient versions of the data structures implementation out there, but we'll not just ignore things about efficiency. We will try to optimize it as far as we can. All right, so in this first video of the series, I'm going to talk about the most basic data structure of all. Well, that is arrays. So what exactly are arrays? Now, like you might think like arrays are a contiguous block of homogeneous data, right? For example, if I declare a static array in C, now one thing I'm going to be working with C++ throughout the course of this series, though whatever I will be saying, it should be mostly applicable to different languages too, but throughout the series we will be working with C++. Now, again, back to the topic, what exactly are arrays? For example, if I declare a static array out there, say array, now let's say an array of size 10, this is a array that can store 10 integers. All right, so in the basic array is a contiguous block of memory storing data. Now, it's something that we can say as a disadvantage of an array is that its size has to be fixed. All right, for example, I've declared a static array out here that has size 10. Now we can also dynamically declare arrays that will, now this is on the this array is declared on the stack. We can also declare it on the heap like this. Right, we can declare it on the heap like this. What this will do is again declare an array of size 10 on the heap. Now, essentially the difference between them is actually how the memory is allocated and how it is being, like for example, in case of stack, we don't actually need to free it ourselves, the compiler will do it. However, in case of memory being allocated on heap, we need to delete it like this. Right, we need to delete it. Now that's a basic difference. Now what I'm talking about is what is common between them. All right, I'm going to talk about, what I'm asking is, what is an array basically? Is it a collection of integers? I mean, like, can this thing only store integers? All right, no, it's not. Basically what this is a contiguous block of memory. What I mean is, it is just a again array, or it is just a series of bytes. All right, now you might know that the computer deals with binary, that is zeros and ones, but that is also, we can say that these individual zeros and ones are the bits of the memory we have, that is the RAM in our computers. Now we can't with modern computers can't really modify or work with individual bits out there. So the minimum amount of data we work with is 8 bits, that is a byte. So what this array is out here is nothing but a series of bytes. Now internally what this looks like will be something like let's say, now uint80 is an unsigned integer of 8 bits. Now that's exactly what a byte is. Now it can be int80, but again I'm going for unsigned types because it will be easier to understand without the negative values. Alright, so what exactly this array out here is, let's say, is array. Now it will be the size of int times 10. Now these two are exactly the same. Alright, array and array 1 are exactly the same in terms of how the computer sees them, right? For now, what do I mean by that? Well, according to the computer, both of these are nothing but a particular amount of memory. For this case, we have got the memory with 10 integers worth of data. That is the size of integer. That will be 4 bytes only, 4 bytes on this computer, and that times 10, that will be 40 bytes. All right, so that's what this array is. Nothing but 40 bytes of data. Again, this too is nothing but 40 bytes of data. Now, what exactly is that? Well, individually, like more specifically speaking, it is nothing but this array is a memory location in our memory, and a promise from the operating system that no one else other than the program itself will modify or read anything from that memory location, but as long as we have that promise. All right, what do we mean by as long as I have that promise? That is, for example, if I declare this array inside a scope, now as long as I am inside this scope, I have got the promise that this array, the memory block of 40 bytes following the memory location pointed to by the variable ARR will not be modified or read by any other program. Now that is a bit different in case of stack and heap, but essentially this is what an array is. All right, now in case of heap, what I mean is I have to manually delete it. That is, we are telling the computer that telling the operating system that we are done with our array, and you can assign it to something else, assign that block of memory to something else. In case of stack, that is just pushed into the stack, and whenever we are going out of the scope, it's going to be popped off of the stack. Now again, there are complicated mechanisms of how these work. There are optimizations on how the array is allocated and where it is placed, and we are not going to talk about that. We are talking about what exactly an array is. So it is just nothing but a sequence of bytes. Now how can we see that? Now again, one more thing you might think is, if the array is a sequence of bytes, again let's come back to our integer array. So array and 10. Now it is an integer array of size of 10. Now if I do this again, now a float array 3 of size 10. Now what exactly is the difference between these two? Well, again, I would say it is nothing. All these three are nothing but 40 bytes of data. All right, again, float is a 32-bit or 4 bytes of data. Int is 32 bits again, or 4 bytes of data. Again, if I say unsigned int array 4, that too is nothing but 30 to 40 bytes of data. All right, because again, unsigned int is 32 bits of data. Now what is the difference? Well, how the data is stored. Now you can learn more about how data is stored by digging deep into how the binary representations are. For example, if I give a brief idea, it would be, in case of unsigned numbers, it will be stored as it is, the binary numbers. In case of integers, that is a signed integer, it will be stored using a technique called 2's complement. And what I'm talking about is the usual case. Now there might be exceptions on different computers. Now in case of floats, there will be there is a standard for defining how exactly the data of a float is going to be stored inside the 32 bits we have allocated with that. Now this is a different topic, so let's come back. Now again, essentially these are bits of data. Now how can we see that? And one more thing, can we really store a float inside an array of integers? Let's try, let's take a look at it. All right, so let me say array 0 equals to 45. All right, so in our integer array, we have assigned 45. But what exactly is array? Array is nothing but an integer pointer. All right, okay, ptr equals to array. All right, so array is nothing but an integer pointer. All right, so for example, what if I do this? If I just say pointer 0. All right, so let's just try and run this. What we expect is having 45 as the output. Let me compile it. Alright, we have got a lot of warnings because we don't really use the variables we have declared. Now we can ignore that. Now again, we are getting 45 as the output. Alright. Now what if I do something like this? If I say float pointer. Now we can see we are getting an error. What is that? A value of type int pointer cannot be used to initialize a value of type float pointer. Now what if we try and compile it? Again, we are getting an error. Now we can actually avoid this error by just so see, we can just avoid that error by typecasting it to float pointer. Now what exactly does that mean? What exactly does that mean? You can see it's getting compiled without any issues. Let's try it and run this. You can see getting a number that is not very relevant to us. Alright, we're getting a number that is not very relevant to us. Again, what exactly is this? Well, this is the 45 is being represented in binary somehow in this array. Alright, so 45 is being represented in binary somehow in this array of signed integers. Now what we do in this statement is we are just telling that reinterpret the value, the array, the memory location pointed to be this array as a float pointer. What does that mean? Well, I'll just tell what exactly. Before telling that, you need to know that this integer, this unsigned integer, this float, where exactly are these needed? I mean, does the computer actually need these data types? No, the computer only works with bytes. Computer has no needs of float or integer or unsigned integer. So where exactly are these data types required we are using? Well, these are just hints to the compiler telling it how is it supposed to perform operations on that. What I mean is, for example, if I say something like array 10 is equals to array, alright, not 10 again, array 1 equals to array 0 plus 1. Now what exactly we are doing? We are just we're storing the value of array 0 plus 1 into array 1. Now how will the compiler know how to interpret this? I mean, there are separate CPU instructions, CPU opcodes for working with integers, for working with floats. Now how will the computer know what opcode to use or what instruction to use in order to perform this addition, right? For example, adding to float numbers have a different opcode instruction than adding to integers. Now how will the compiler know? Compiler will know that using this. Now there are rules. For example, if I try to add a float with it, now a compiler will decide what compiler will decide to convert one of them to implicitly to one of the types and then to perform the addition and perform the operation. Now that's complicated things that is managed by the compiler. Well, what we're talking about is this data types. These are nothing but hints to the compiler about how it's going to perform operations with these variables. Now what I'm talking about is strictly for C and C++ out here for now. Now these can be these ideas can be extended to some other languages, but I'm strictly talking about C and C++. All right, now again, this is just as these are just hints to the compiler. We can tell the compiler no longer think that ARR is pointing to a array of integers, rather pointing to an array of floats. Again, what I say is this array is nothing but a pointer. All right, a pointer to a memory location. Now that has got nothing to do with float pointer, integer pointer. All these are nothing but an integer. I mean, a pointer is nothing but an integer. All right, so all of these are pointing to a memory location. Now how we treat the memory in that memory location or in that block of memory is up to us. Now if whenever I'm typecasting this into float pointer, or in C++ we can do something like let's say reinterpret cast float pointer. We can just do this reinterpret cast. Again, we'll get the same result. Let's just compile it. All right, let's just compile it and see that. Again, we can see we get the same result. Now we are just doing it in a more C++ way. All right, so you can see that we are just telling that compiler to think of that block of memory now as floats. Again, we can see that we can store floats in that. Now what if I try and do this? All right, so if I say now after this, if I say ptr 0 is equals to say again of 32.0f. Now assigning a float value, we can see we are doing it fine. Now what if I just try and print out again arr 0? Now what do you expect to happen? Let's see. Alright, so you can see we are getting 32. Now 32 again, it's not. Let's do something like this so that we can see the clearly see it's a floating point number. Alright, so let's clear it up. Alright, we can see that we are getting the floating point number that is correct representation out here. However, we can see we are getting an absurd integer out here. Now why is that happening again? Well, that's because that's because we are storing a float in there. Now floating point numbers are stored in a completely different way from how integers are stored, right? So like again, that does not make sense. So we are getting something, but like the memory the memory is being read as an integer. However, we are storing a float out there. But again, we are storing a float, but still we can interpret it as an integer, right? So we are getting this absurd value out here. Again, what if I try to see what exactly is inside all these? How to see that? We can see the value of the individual bytes out there. So you can say again unsigned integer 8 pointer, say bytes. We can say reinterpret cast this again. Sorry, we can cast this again as unsigned pointer e. Right, so you can see the bytes now. Let's just try and see the bytes. Now I'm going to talk about the first 4 bytes, the storing the value of one integer. Now the same thing applies to the entire thing. All right, so let's just try and see the first 4 bytes. All right, so bytes 0 space, again let's just copy and paste that. All right, so we can say that bytes 0, 1, 2 and 3. Let's see what exactly we are getting in the bytes. Okay, let's compile it first. Alright, so if we just build it, we can see okay. Now the bytes are again, the issue is, let's just see that the issue is that the bytes are being printed as characters rather than the integers. So we have to just typecast them to integers. Alright. Now you can do static cast or anything else, but this is a shortcut. We were just trying to debug what exactly is happening behind the scenes. So alright, so we can go with this. Now let's compile it again. Okay, compilation is about to be done. Alright, compile. Now if we just run it again, you can see these are the 4 bytes that are being stored. Now again, there is one more catch out here. How are these bytes stored? Now it's like you might find that in your computer the bytes are stored in a different way. What do I mean a different way? It will be 66, 1, 212, 254 in a reverse way. Well, that's too possible, and that's too a valid thing. Why? Again, how computers store the bytes is again a matter of the processor you're using. That is the I'm not remembering the term, but again it's called the byte order. Right, it's called the byte order. Now the byte order might be little endian or big endian. What do I mean by little endian? By little endian, I mean the most the most significant byte will be at first, and in one the least significant byte will be at first. Now different processors use different byte orders. Again, you might see this order of bytes in a reverse way in your own computer, because your computer uses a different byte order. All right, so again, there are conventions for that, but as we can see that these bytes itself, like these arrays and everything, are individually bytes. All right, so this was an important thing, because we need to know how these work in order to work with further data structures. Again, like sometimes we might just share, like push in a float value inside an integer, or sometimes you might see that, and like 4 by in case of, if you are working with pictures, image processing, sometimes you might see something like an integer holding the RGBA values of a pixel, like an integer, a single integer holding an RGBA value of the pixels. How? Because RGBA values 0 to 255, usually they are 0 to 255, right? Again, we can store 4 now 0 to 255 can be stored inside a single unsigned integer. All right, a single 8-bit unsigned integer, that is uint 8t. Now an integer has the size of 32 bits. Now an unsigned 8 integer has a size of 8 bits, so we can easily store 4 unsigned 8-bit integers inside a int. All right, so again, we can store all these pixel value, like all the colors of the pixel inside a single integer. That's also interesting thing. Now you will see, if you're trying to implement some VMs, you will see entire opcode being along with it, the opcode ID, the parameters, everything being stored inside a single integer. Again, these are stored like using the space available directly, rather than using separate integers or separate bytes. All right, so that's what we have got in the arrays part. The next thing is we are going to talk about is dynamic arrays. Now, as you can understand, one of the biggest disadvantages of this array is the fact that it has a fixed size. You sometimes you don't really know how big your data is going to be. For example, you're reading a file. Now you don't really know how big your data is going to be. For example, you're transferring a data, like something over the internet. You don't really know how big your data is going to be. Now you can obviously send the size and all, but again, there are cases where we don't really know how big our data is going to be. For example, you're taking input. Now how long is the input going to be given? We don't really know that. So we need something that doesn't really has a limited size, but also can grow according to our needs. All right, so we need that's something that need is satisfied by something called a dynamic array. What exactly is a dynamic array? In C++ itself, we have got something like vector, the class called vector. Now what exactly vector does is, we can say std vector. Now we need to provide a type, select integer and vec. Now we can just say vec dot pushback and 10. Now we are not really, you can see we are not really providing vector with a size. Now we can provide vector with a size to pre-allocate it and stuff like that. We will see that a bit later. Now you can see we just pushing back a value in the vector. Now we can also access that value by vec 0. It's like a normal array, but it doesn't matter if I do this once or if I do this say for if I do this 100 times. It doesn't matter if I do this one time or 100 times, this is going to be working, because the array will grow, like the vector size will automatically grow as our data increases. Now this is very important data structure. So alright, for that's it for this video. In the next, we'll be trying to implement a dynamic list or a dynamic array. Well, what is that? Well, it will be an array, but overcoming the traditional problem of an array, that is not having a fixed size. So we'll make an array that is having that will be growing dynamically, and also will be able to automatically handle expansions. What I mean is, if we are trying to access a variable, access an index that is not allocated within that scope of memory, it will automatically allocate more and initialize that, and we'll have that scope of memory. All right, so we'll be implementing something like that. Now if you are familiar with some other programming languages, you might know it as something called lists. For example, in Python's default list is something like a dynamic array. Same for JavaScript's array. Also like in Java, you've got the array list in Java, and I think in C# too. In C++, you call it vectors. So we'll be implementing something like that in our next video. All right, thanks for watching.